You have counted 12 full moons since the last great salmon run. So your group leaves the winter shelter and begins walking toward the river. The journey takes 3 days. Children carry baskets. Hunters carry spears. The oldest members of the group carry the memory of where the fish should appear. But when you arrive, the river is almost empty. Snow still clings to the shaded banks. The insects have not emerged. The salmon are not there. If you wait, your stored food may run out. If you return home, another group may reach the river first. And if the fish arrive after you leave, the mistake could cost your family an entire season of food. You counted correctly. 12 moons have passed. So why is spring late? Because the moon and the seasons are keeping different time. 12 lunar cycles last about 354 days. The solar year lasts a little more than 365. The difference is only around 11 days. But 11 days is enough to miss a migration plant too early. Arrive after a herd has moved or hold a ceremony under the wrong sky. After 3 years, the error grows to roughly 1 lunar month. The moon has not failed. Your system has. This is the problem that eventually created calendars, clocks, minutes, seconds, time zones, and the numbers glowing on your phone. Not the problem of knowing whether it is morning or night. Animals can do that. Your body can do that. The deeper problem is making different people agree about a moment that has not arrived yet. When should we meet? When should we leave? When should the field be planted? How long has the worker labored? How late is late? Humans did not invent time. The universe was changing long before we existed. What we invented was a shared system for cutting change into pieces, carrying those pieces into the future, and forcing strangers to recognize the same invisible schedule. The first clock was not a machine. It was a prediction. And the first thing humans discovered was that the sky contains several clocks and they do not agree. Long before anyone divided a day into hours, human life was already surrounded by rhythm. Light returned after darkness. Tides rose and fell. The moon changed shape. Animals migrated. Plants flowered, fruited, and disappeared. The body carried its own cycles too. Hunger, sleep, menstruation, pregnancy, the gradual weakening of age. You did not need a number to know that the fire was dying or dawn was near. You could hear birds begin calling. Feel the air cool before sunrise. Watch a familiar star sink toward the horizon. Time was not an abstract line extending endlessly in both directions. It was a collection of events. The time to gather shellfish. The time when shadows reach the rocks. The time after the first frost. The time it takes to cook meat. The time since a child was born. In this world, duration was often described through another process. A meeting might happen when the sun touched a ridge, not at 5:30. A task might last until the basket was full, not for 8 hours. This kind of time is flexible because nature is flexible. A hunt ends when the animal is found. A journey takes longer in rain. Work follows the task rather than the clock. But flexibility becomes a problem when cooperation expands. The more people involved, the more costly disagreement becomes. One family sees the first crescent tonight, another sees it tomorrow. One group calls this the beginning of spring. Another waits for a particular bird. Memory also fails across long spans. How many moons have passed since the last flood? Was the winter before a child's birth colder than the winter after it? Did the herd arrive before or after the moon became full? A human brain can remember stories. It is less reliable at preserving identical intervals across generations. So, people began placing time outside the body. A notch, a stone, a repeated mark, a path aligned with sunrise, a place where the changing sky could be compared with something that did not move. The invention of timekeeping began when humans stopped merely experiencing cycles and started building objects that could remember those cycles for them. In 1976, an aerial photograph was taken above farmland near Craiths in Aberdeenshire, Scotland. The image showed differences in the crops. Plants growing over buried soil disturbances can rise differently from plants above undisturbed ground, revealing shapes invisible from the surface. One of those shapes belonged to a Neolithic timber hall. Nearby was something less impressive, a curved line of pits. When archaeologists excavated the area, they found 12 certain pits, arranged from smaller features at the ends toward larger ones near the center. Some pits were more than 2 meters across. Several had been cut again and again over long periods. The alignment was far older than the nearby farming structure. Its earliest form dated to the early 8th millennium BCE, when the people living in this part of Scotland were hunter-gatherers. At first, the pits did not announce their purpose. They contain no clock hands, no written month names, no instruction manual. Then archaeologist Vincent Gaffney and a multidisciplinary team began looking at the pattern differently. The pits formed an arc. Their sizes rose toward the middle and fell again, resembling a symbolic sequence from a thin crescent toward a full moon and back. There were 12 of them, and the central area pointed southeast toward a break between hills known as the Slug Road Pass. Using digital terrain data and specially written visualization software, the researchers reconstructed the horizon as it would have appeared around 8000 BCE. At midwinter, the sun rose through that break. The pits appeared to combine two systems. The changing sizes may have represented lunar phases or months. The midwinter sunrise could provide a yearly reset. In 2013, Gaffney and his colleagues described Warren Field as a possible luni-solar time reckoner, perhaps the earliest built structure currently known that was used not only to respond to an astronomical event, but to anticipate time to come. The interpretation remains hypothetical. A line of pits cannot tell us exactly how people used it, and the researchers themselves warned that symbolic resemblance is not proof. But the idea solves a real problem. If a marker moved from pit to pit with each lunar month, the community could count the moons. Then, once each year, the midwinter sunrise could reveal whether the count was drifting away from the seasons. The field did not make time visible. It made error visible. And that may have been the first great purpose of a calendar. The problem at Warren Field never disappeared. It only became more organized. A lunar month lasts about 29.5 days. 12 of them produce a year of roughly 354 days. But the seasonal year, the time Earth takes to return to the same position around the Sun, is about 365.25 days. The difference is small enough to ignore for a while. That is what makes it dangerous. A bad clock that loses half the day immediately is easy to reject. A calendar that loses 11 days each year can appear correct until the seasons begin sliding beneath it. Human societies developed different solutions. Some inserted an extra month when the drift became obvious. Others built calendars around the sun and allowed lunar festivals to move separately. In ancient Egypt, a civil calendar of 12 30-day months was in use by at least the middle of the 3rd millennium BCE. 5 additional days were added to reach 365. It was elegant. It was also still short, by roughly a quarter of a day. Without leap years, the calendar moved slowly through the natural seasons. A date tied to harvest would not remain tied to harvest forever. The Egyptians could also watch Sopdet, the star we call Sirius, whose reappearance in the dawn sky occurred near the annual Nile flood. The star, the river, the moon, and the official calendar created overlapping systems rather than one perfect answer. This is a pattern repeated throughout the history of time. No natural cycle divides cleanly into every other cycle. The day does not fit perfectly inside the month. The month does not fit perfectly inside the year. The year does not contain an exact number of days. The Earth itself does not rotate with absolute uniformity. Timekeeping is therefore not simply observation. It is negotiation. Humans choose which cycle will serve as the authority, then invent corrections for everything that refuses to fit. An extra day, an extra month, a leap second, a rule announced by priests, rulers, astronomers, or international committees. A calendar looks like a description of nature, but every calendar also contains a decision about which mismatched society is willing to tolerate. A calendar can tell you when the flood season should begin. It cannot tell 2 workers when to change shifts during a single day. For that, humans had to cut the day into smaller pieces. Ancient Egyptians divided daylight into 12 hours and darkness into 12 hours. At night, groups of stars known as decans could help track the passing intervals. But these were not the equal 60-minute hours, you know. Summer daylight lasts longer than winter daylight. If every day is always divided into 12 daylight hours, then a summer hour must be longer than a winter hour. Time stretched with the season. That made sense while the sun remained the clock. Beginning around the New Kingdom, roughly 1500 BCE, Egyptian evidence includes sundials, shadow clocks, and water clocks for measuring these hours. A shadow clock turns movement into geometry. A raised bar or projection casts a shadow across marked divisions. As the sun crosses the sky, the shadow changes direction and length. The user does not need to understand Earth's rotation. The ground itself becomes a dial. But sunlight is not an obedient mechanism. Clouds erase the reading. The shadow changes with latitude and season. Near noon, its movement behaves differently from the long morning and evening shadows. A device may need to be turned around or read through different scales during the day. and the clock cannot work at night. Still, the psychological change is enormous. Before the shadow clock later belongs to judgment. After the shadow clock later can be pointed to. A priest can say a ritual begins when the shadow reaches this mark. A supervisor can say a shift ends at another. The mark becomes a third witness between two people. It can settle disagreement or create it, because once an interval is represented outside the body, someone can accuse you of arriving after it. The clock does not merely reveal a moment. It creates a standard against which behavior can be judged. But the sun still controlled the standard. To make time continue through darkness, humans needed something on Earth that moved steadily enough to imitate the sky. At the Temple of Karnak in Egypt, archaeologists found a vessel unlike an ordinary bowl. The original, discovered in 1904, dates to the reign of Amenhotep III around the 14th century BCE. It was made from stone and shaped like a container with sloping sides. Inside were scales arranged for different months. Near the bottom was a small opening. Water was poured into the vessel. Then it escaped. As the level fell past the marks, the user could estimate the hours of the night. This was a clepsydra, a water clock. Its principle appears simple. A container begins full. Water flows through a hole. The falling surface measures duration. But water does not leave a vessel at a perfectly constant rate. When the container is full, greater pressure pushes the water out faster. As the level falls, the flow slows. The shape of the bowl and the spacing of the marks must compensate for that changing pressure. The Karnak clock also had to account for seasonal hours. Because nights lengthened and shortened across the year, the vessel used different scales for different months. This was not merely a bucket with a hole. It was an attempt to model an invisible interval through controlled physical change. The water clock solved problems the shadow could not. It worked indoors. It worked at night. It could measure a speech, a guard shift, a ritual, or an astronomical observation without waiting for the sun. Yet it introduced a new relationship with time. A shadow is tied to the world outside. Water can be started by a person. The interval begins when someone fills the vessel. For the first time, a small artificial process could be made to stand in for a much larger celestial one. The clock no longer had to display where the sun was. It could manufacture a duration of its own. That separation would eventually allow clocks to keep running when the sky was hidden, when seasons changed, and even when the planet itself proved irregular. But the units were still not hours. An Egyptian hour changed length. There were no ordinary minutes or seconds. To create those, time had to meet a number system built for division. The number 60 is hiding everywhere in your day. 60 seconds, 60 minutes, 360 degrees in a circle. This is often explained with one sentence: the Babylonians invented our clock. The truth is more complicated. Ancient Mesopotamian mathematicians used a sexagesimal or base 60 place value system for advanced calculation. 60 is unusually convenient because it can be divided evenly by many smaller numbers. 2, 3, 4, 5, 6, 10, 12, 15, 20, 30. That makes fractions easier to express. Babylonian astronomy used sexagesimal numbers to record and calculate celestial motion. Greek astronomers inherited and expanded those methods, applying subdivisions to angles and astronomical coordinates. But ordinary Babylonian life was not organized by a modern clock face with a minute hand. The path from base 60 to 60-minute hours took centuries. Scholars divided quantities into increasingly small fractions. In medieval Latin, 1/60th could be called the pars minuta prima, the first small part. Divide that part by 60 again, and you reached the pars minuta secunda, the second small part. That is why a second is called a second. It was the second level of division. For a long time, these tiny units belonged mainly to mathematics and astronomy, because everyday devices could not display them usefully. What would a second mean to a farmer using a shadow? What would a minute mean if the hour itself changed length with the season? Fine units become socially important only when machines can repeat them and communities have reasons to care. This is the hidden rule behind precision. Humans do not measure more accurately simply because accuracy is intellectually satisfying. They do it when mistakes become expensive. Astronomers need to compare observations. Navigators need to calculate position. Merchants need appointments. Institutions need schedules. Employers need to price labor. A smaller unit is a sharper promise. It allows two people to disagree by less. It also allows one person to control another more precisely. The number 60 supplied the divisions. but it would take gears to make those divisions march through ordinary life. In 1900, Greek sponge divers sheltering near the small island of Antikythera encountered a Roman-era shipwreck. Working in heavy suits with air hoses and the assistance of the Greek Royal Navy, they recovered statues, glass, jewelry, pottery, and corroded pieces of bronze. The spectacular sculptures drew attention. One dark lump did not. Then in 1902, Spyridon Stius noticed a gear embedded inside the broken bronze. The object should not have existed. Its triangular teeth belonged to a mechanism far more complex than historians expected from the ancient Mediterranean. The fragments became known as the Antikythera mechanism. Researchers spent generations trying to understand it. In the 20th century science, historian Derek de Sola Price argued that it was a geared astronomical calculator. Later X-rays, gamma imaging, and high-resolution computed tomography revealed hidden teeth and inscriptions beneath the corrosion. The surviving pieces contained dozens of bronze gears. By turning a handle, the user could model cycles in the sky. The mechanism tracked lunar and solar calendars. It represented the irregular motion of the moon. It could indicate eclipse cycles years into the future. Its dials also connected astronomical time with civic events, including cycles associated with athletic games. The Antikythera mechanism was not a clock that told you to meet someone at 3:15. It did something psychologically deeper. It placed the future inside a box. A user could rotate the machine forward and watch a predicted eclipse approach. Time was no longer only remembered from the past or observed in the present. It could be mechanically explored. The sky had been translated into gear ratios. This is the same intellectual move seen at Warren Field but compressed into bronze. The pits used landscape moon and sunrise to correct one another. The mechanism used interlocking wheels. Both solved time by linking cycles. Both turned prediction into an object. And both reveal that early timekeeping was rarely about punctuality. It was about dangerous events that had to be anticipated. Winter, floods, eclipses, festivals, the return of a season. A clock becomes valuable when the future contains something you cannot afford to miss. The first mechanical clocks appeared in Europe during the second half of the 13th century. Their defining breakthrough was not the gear itself. Gears had existed much earlier. The crucial element was the escapement, a mechanism that released stored energy in controlled steps. A weight pulled downward. The gear train tried to spin. The escapement repeatedly stopped and released it. Tick, pause, tick. The machine converted a continuous force into counted intervals. Unlike the sun, it did not care whether the day was long or short. Unlike water, it did not gradually lose pressure in the same way. Mechanical clocks made equal hours practical. At first, many public clocks announced time through bells rather than hands. Most people did not need to own a clock. They needed to hear one. The bell could summon worshippers, open markets, close gates, organize meetings, and coordinate labor across a town. This changed where temporal authority lived. The sun belongs to everyone who can see it. A public clock belongs to whoever maintains sets and controls it. If the bell rings, the town moves. Historian E.P. Thompson later described the long shift from task-oriented work toward clock-oriented discipline. The transformation was neither instant nor identical everywhere. People did not suddenly stop following daylight weather animals or the needs of a task. But equal mechanical hours made a new arrangement possible. Labor could be purchased as duration, not simply a completed object, not simply a harvest brought in, an hour of another person's life. The clock turned time into something that could be counted, sold, withheld, wasted, or stolen. This is why clock language sounds economic. We spend time, save time, waste time, invest time. The machine did not create those human concerns by itself, but it gave institutions a device capable of enforcing them. A late hunter may miss prey. A late factory worker violates a number. The difference matters. Natural time punishes you through consequence. Clock time can punish you through authority. And once society depended on equal hours, the next demand was unavoidable. The hours had to become more accurate. By the 17th century, mechanical clocks could count equal hours, but they were still imperfect companions. Friction changed. Temperature changed materials. Escapements disturbed the oscillation they were trying to measure. A clock could gain or lose many minutes in a day. That was good enough to ring a bell. It was not good enough for increasingly precise astronomy and navigation. Christiaan Huygens looked for a process in nature that repeated itself more evenly. He found it in the pendulum. Galileo had studied the regularity of swinging bodies earlier in the century. Huygens turned the principle into a practical regulator. In 1656, he designed a pendulum clock, patented the design the following year, and worked with clockmaker Salomon to build it. Rijksmuseum Boerhaave in Leiden still preserves Huygens's first pendulum clock. The pendulum offered a bargain. Gravity pulls it toward the center. Momentum carries it past. The swing repeats. Connect that repetition to an escapement, and the pendulum controls when the gears may move. The clock no longer asks the gear train to create regularity. It borrows regularity from an oscillator. This is the central idea behind almost every precise clock that followed. Find something that repeats. Count it. A pendulum. A vibrating quartz crystal. An electromagnetic transition inside an atom. The material changes. The logic remains. Better accuracy altered human behavior. Minute hands became useful. Scientific experiments could compare shorter intervals. Astronomers could record events with greater precision. Ships needed reliable time to determine longitude, turning clock accuracy into a matter of survival and empire. But precision also narrowed the acceptable space around a promise. Meet me in the afternoon allows both people to be approximately correct. Meet me at 3:07 creates one winner and one late arrival. A more accurate clock reduces uncertainty. It also reduces mercy. Humans built precision to coordinate better. Then we began judging ourselves by the precision we had built. For most of history, noon was local. It happened when the sun reached its highest point above your town. Move east or west, and noon changed. That caused little trouble when travel was slow. A neighboring town could be several minutes ahead, but a horse could not make the difference operationally dangerous. Then trains began moving people faster than local time could remain simple. Railway schedules crossed dozens of communities, each using its own solar noon. A station might display several clocks for different railroads. A timetable could require passengers and conductors to translate between competing local standards. The telegraph made the contradiction sharper. A message could move almost instantly between places that disagreed about what time it was. The problem was no longer measuring the sun. It was deciding whose noon would count. On the 18th of November, 1883, North American railroads adopted a system of standard railway time. At a coordinated moment, clocks were reset into large zones. Local solar time did not vanish because astronomers disproved it. It lost authority because networks had become more important than towns. The railway turned time into infrastructure. A shared clock reduced missed connections and collisions. It also demonstrated that official time could be changed by agreement. People complained that minutes had been taken from them. In one sense, they were right. A town that had lived by its own sun was now told to obey a distant meridian. Time zones are so familiar that they appear natural. They are not. The lines bend around borders. Governments move them. Countries choose half-hour or quarter-hour offsets. Political decisions can place enormous regions under one official time, even when the sun crosses them at very different moments. The clock had completed a reversal. At first, humans built devices to follow the sky. Now society adjusted the meaning of noon to serve the network. Time no longer told railways when to run. Railways helped decide what time was. Even standardized clocks remained tied to the Earth. A second was ultimately derived by dividing an astronomical cycle, the day, later the year. But Earth is not a perfect clock. Its rotation shifts slightly because of tides, changes inside the planet, atmospheric motion, and other effects. The world needed a rhythm more stable than the world itself. Physicists found one inside atoms. Atoms of the same isotope respond to radiation at extremely consistent frequencies. Instead of watching a shadow move or a pendulum swing, an atomic clock tunes electromagnetic radiation until atoms respond. Then it counts the cycles. In 1967, the international definition of the second changed. 1 second became the duration associated with exactly 91926317770 periods of radiation, corresponding to a transition in cesium-133. The decision reversed the ancient relationship. Minutes and hours were no longer defined primarily as smaller divisions of the solar day. The day could now be measured as a collection of atomic seconds. The clock had become more authoritative than the sky it was invented to follow. Modern navigation satellites depend on this precision. So do telecommunications, electrical networks, financial systems, and technologies that coordinate actions across the planet. Your phone may display time casually. Behind it stands a global system comparing clocks so stable that tiny disagreements matter. And yet the language still carries fossils from an older age. A minute comes from the idea of a first small division. A second is the second small division. The words remember scholars cutting circles and hours into 60ths long before ordinary people owned devices capable of noticing either one. Return to the empty river. You counted 12 moons. The salmon did not arrive. Your mistake was not stupidity. It was trusting one natural rhythm to predict another. Every clock since then has been an attempt to solve the same problem. The pits at Warren Field linked moon to midwinter sunrise. Egyptian clocks linked shadow and water to ritual hours. Babylonian and Greek mathematics divided cycles into portable numbers. The Antikythera mechanism linked gears to eclipses. Mechanical clocks replaced seasonal hours with equal ones. Railways replaced local noon with network time. Atomic clocks replaced Earth with cesium. Humans did not invent time. We invented increasingly powerful agreements about which repeating process everyone else must obey. Those agreements allowed strangers to meet cities to coordinate ships, to navigate experiments to be repeated, and satellites to locate you. They also created deadlines, lateness, wages by the hour, alarms, schedules, and the quiet feeling that a number is chasing you. The first clock helped humans survive a season. The modern clock can divide your attention into seconds. That is the hidden cost of mastering time. We built clocks so the future would stop surprising us. Then we began living as though the clock owned the future.